Okay, good morning. This is our first AEM341 Microbiology Lab. Since we are doing microbiology, so obviously we're going to use a microscope first. So we want to tell you the principles behind that, and you're going to get a chance to practice. Okay, so what is microscope? What we are doing here in the lab is light microscope. And for this specific microscope on your bench, this is called bright field. So what this means? This means underneath the specimen, you will see the sample which is colored. Well, of course, you have to do the stain. Okay, that's what we will do later on. And the background is like white. So that's called bright field microscope. So we want to talk about the several principles about a bright field microscope. I know you learned in your other classes a lot already, but there's something we still want to emphasize, so that's why we want to talk about that. Okay, first thing first is magnification. We talk about this total magnification. So first of all, microorganism is too small to see. So we need using a microscope. Now, the first question I want to ask you is, if you look at your microscope, what do you think which part is the most expensive one? Is the lens, is that right? Yeah, we have two lenses, you will see. One is you can using your eye attached to it. That is called the ocular lens. Another one is the lens which will touch the specimen. That is called the objective lens. And the magnification of the ocular lens and the objective lens, we multiply them, we'll get total magnification. So it's a very simple question. What is the magnification of the ocular lens? The microscope what you use is always 10x. Now how about the objective lens? If you look at your objective lens, you will see there is a 4 different type, which is 4x, 10x, 40x, and 100x. So you can do a math. If the objective lens is 10x, so what is the total magnification? It's 100x. If the objective lens, the magnification is 100x, then the total magnification is 1000x. Okay, this is the first question, the total magnification. The reason is microorganism is too small to see. We have to magnify. Okay, that's the first question. Second question, what we talk about is called working distance. So if you look at your microscope, you will see there is 4 different types of the lens. We already mentioned. Well, I'm talking about is objective lens. Okay, let's say this is stage. Then you will have 4x, 10x, 40x, and 100x. What is called working distance? That is the distance between the objective lens to the stage. And you can see the working distance is obviously decreased with the increasing of the magnification of the objective lens. So working distance is decreased with increasing of objective lens, magnification. So that's the second point we want to talk is a working distance. We will mention later on why it is important. Now in this class, start from now to the end of the semester, we will always use using 10x to find a specimen, then using 100x with oil immersion to find the morphology of the bacteria. We will never use 4x. And the 40x is only one time when we do the yeast and modes. Barely we're going to use it. Okay, so these two we do not use in this classroom too often. We will focus on these two. So that's the second concept. The third concept is called parafocal. So what is parafocal? Like I just mentioned, we're going to use 10x and 100x objective lens. So once you use 10x to find the specimen, which means it's focused, then you put the oil there, and then you switch to the 100x. The lens will stay focused, which means you only need to do a very minimal adjustment. So what means parafocal? That means once focused, objective lens stays focused. Very simple. So if you want to transfer this language, that means if 10x objective lens focused, switch to 100x, only need minimal adjustment. That is called parafocal. The parafocal, this concept is very interesting and very important for the light field microscope what we are using, and it's an advantage. Because otherwise, when you go to the 100x, you have to refocus. It's spending another huge time to refocus. Once it stays focused, you don't have to do it again. Okay, so that's a good advantage. Number 4 we want to mention is called oil immersion. You heard about it before, even in high school. When we do a microscope observation to observe bacteria, if you said you use a 10x, then you switch to 100x, you find it's not even clear. It's going to be more fuzzy even. Then your teacher will say, okay, put 1 drop of the oil there. And then you follow the procedure to do, you find you will see the morphology of the bacteria. Then why we can do that? So the story is, this is the air, this is the glass, air, and go to the glass again. When the light going through a different medium, go here, okay? So you go here, go here, go here, same thing here, here, and go here. What something will be happen? What we call is in the physics, what's the terminology? Called the light refraction. So very simple example. If you have a bottle of water, this is water, let's say. I'm going to put a pencil there. When you see through the glass bottle, what you see? This pencil is blended, is bended. Is that right? It looks like. This is the light refraction. The reason is light going through the air, go to the glass, then go to the air again, and go to the glass again. During the different mediums, it causes refraction. When the refraction generates and you switch 10x to 100x, the reflection is even magnified. So you find it's going to be more fuzzy when you switch to 10x to 100x. So how to solve the problem? We're going to put one drop of the large oil. Why? Because the refraction index of air equals 1.0. The refraction index of glass equals 1.5. And the refraction index of oil also equals 1.5. So when you put out one drop of the oil, what this means? That means you connected the glass and the oil, make the whole system, and remove the air gap. That is the air gap you removed. Therefore, you minimize the light refraction. Okay, so what's the oil immersion? The function is remove air gap. Minimize light refraction. Okay, so that's called oil immersion. The last concept, number 5, is called RP. So write the formula for that. RP equals lambda divided by 2 and NA. Okay, what does RP means? R means resolution. P means power. So RP is the acronym of resolution power. Now what is lambda? The lambda is always equal 625 nanometer. What is NA? This NA means numerical aperture. Where it is? If you look at your 100x objective lens, you will see somewhere around here, on the side of the lens, you will see it's right oil and 1.25. This 1.25 is called numerical aperture. I always call this is like a size of the engine, like the size of your car engine. Okay, so that is called the size of the engine. Therefore, we could do a calculation. What is our resolution power of the microscope we're using? That is 625 divided by 2 multiplied by 1.25. What is the number? 260 nanometer. Sorry, 260 micrometer. Nanometer. That equals 0.26 micrometer. Okay, what this number means? I'll give you an example. Can you guess what is the average size of a microbacteria? We're going to do observation in the lab. Let's say a Staphylococcus aureus. What's the average size? It is about 0.5 micrometer. Your resolution power is 0.26. This is less than that. Therefore, we couldn't use this light field microscope with oil immersion to observe the morphology of Staphylococcus aureus, because the resolution power is lower than the size of the bacteria. Then what is the average size of a virus? Let's say HIV virus. What's the average size? 0.01 micrometer. That means 10 nanometer. And this number is less than the resolution power of the light field microscope. So therefore, we cannot use light field microscope to do the observation of a virus. What we have to do? We have to use electron-analyzed microscope or electron microscope. That's the reason. Because the resolution power has to be smaller than the subject. What are you to do the observation? The resolution power, you can say easily, is a capability to differentiate the two particles when they're very close, attached very close. Okay? So always remember that. That is called resolution power. Now, obviously, the resolution power should be the smaller, the better. That depends on the lambda. Now, all our microscope has been fixed is 625 nanometer. We can change it. Okay? So that is all these concepts which we talk about. Is a light field microscope, how we're going to use it. Okay, now, the next one, I'm going to show you how to use a light field microscope. So, let's all come here. I will use this one as a demo. Okay, everybody come here. I'll show you how to do it. Sorry. So today's work, we will be using a meted microscope, which means a meted slides, a bacteria is already there. So let's say you have a Staphylococcus aureus is right there. And we're going to pick one. Okay, we have all these. And another one is the budding yeast. So right here you can see it. A stained with crystal violet. So how to do it? This is the microscope. Obviously you will see the ocular lens, objective lens, and you can switch. Is that right? And then you see the red one is 4x, yellow one 10x, blue one 40x, and the white one is 100x. If you look very carefully, you see the 1.25 there. That means the numerical aperture, which is like the size of the engine of the microscope. Okay, this is the stage control. You can move back and forth. This is the SICK one, the SICK knob, which is up and down to control the stage. This is called coarse focus. And this is the thin one, the knob, which is the fine focus. And when you first use a microscope, don't forget about to plug in. Because lots of people said, I cannot find anything because you forget to plug in. This guy you have to turn or on. And the power has always be at the end. This light, the lambda, is 625 nanometer. If you do like this, it will be probably 800-ish or something. So you make sure it's all at the end. Some of the microscopes, there's a control panel right here. You can adjust the amount of the light, but this one you cannot do. Another thing very important is back here, you will see. This guy you can move around. This is called iris diagram, which means they can control how much amount of the light going through the lens going to the specimen. And if you use 10x, you always put at 10x. When you use 100x, you always go to 100x. Okay? So, how are we going to do this? First of all, this stage will be staged down. We are doing like this. Then, we're going to put a slides there. The slides right in here, we're going to switch them into the middle. Okay. Then you're going to have this guy right there. So use 10x. Now you eyes there, all the way up, 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 to the place you cannot move. All the way up. It will not break it. There's a difference. There's a distance between the objective lens and the slides. So then what you do is go slow down. Go down, go down, go down a little bit. Go down a little bit. Then you can see something. Go ahead to see what it is. You can see something. Is that right?
Yeah.
Okay, come here to see what it is. I'll give another student to see. Can you see it? You can see something.
Yeah.
Not very obviously, but you can see something, at least some there. But what you do, you're going to put the oil immersion to see the morphology. This is the oil. What we do, 2 hands right here, do a switch. Make sure there's a space. This is 40x, we don't use it. Skip this one, goes here. Make sure there's a space between that, then you got to put the oil. The oil has to be a huge and a large drop. Not a tiny one, okay? When you put the oil there, what we do? Then go to 100x. Now, this guy has to move, the iris diagram has to be adjusted to 100x. Then what you do is you only need to do a very tiny adjustment and you can see the morphology. Go ahead to see it. You will see it looks like a grape and a stained purple. And it's a cocktail. It's a round shape because Staphylococcus aureus. Come here to see it. It's your turn. Can you see it?
Yeah.
Yeah. That's what you do. Now, what you're going to do is on your notebook, you're going to draw the picture there, what you find. And you also, if you have a cell phone, it's difficult to do. You can take a picture like this. And just print it out, put on your notebook. This will be the first trial of using your microscope. When you finish this, you also get another slide. This is the budding yeast. This guy is Saccharomyces cerevisiae, which is using for beer brewing. We talk about later a little bit when we move to the fermentation, but you get to know what is the difference between these two things. This is a yeast. It's a eukaryote. That is a prokaryote. It's a bacteria. Okay, so that's going to be you to practice. And I hope you get familiar with the microscope, how we're going to use it. Because we will do simple stem on Thursday, gram stem on next Tuesday, and endosperm stem next week. And then we have a quiz, which means a group project to do the unknown. The next 5 lab, we all going to use a microscope. And I would love you, at the end of the day, come out of this classroom, no matter which grade you get, you are very comfortable and have a big confidence to use microscope. And you will be the master of this. Okay, that's a goal. So go ahead to practice. If you don't know how to do it, you can ask TA. He will help you to do that. Okay?